So this is going to be the problem for 322, MAE 322. This is with Dr. Lee's class. I was given permission by her to use this problem from the homework. This one's pulled from homework 2. I think it's the first problem. So let's get at it. So part A is asking us to find the normal and shear stresses at A and B and draw the stress cube. Part B is asking us to find that maximum normal stress value and the location as well. So we start with an L-shaped circular beam. So we're gonna have that its radius is 0.5 inches, and we're gonna have this cross section existing here with my X going in that direction, Y going in that direction, my Y going in that direction, my Z going in that direction. I'm gonna have also my force acting over here. It's 9 inches away in the negative X direction and 3 inches up in the Y direction. They're acting on negative 2400, positive 600, and positive 400. So let's try to answer that first question. Find a normal and shear stress at point A and B and draw the stress cube. So first, how do we find that normal stress? So my formula for normal stress is going to be my axial stress plus my bending stress. Cool. My axial stress, let's deal with that one first. So my axial stress is going to be that basic definition of stress, which is force over area. In this case, we're going to find that it's going to give us that force, which is 2400, divided by that area, which is going to be pi r squared. So, some points that I do want to say. I am using positive 2400 here because I know that this guy is going to be tension. We're just going to be pulling it out. And we usually say that tension is positive, so I'm forcing it to be positive. When I plug this into my calculator, I should be getting positive, what is that, 3.056 psi. I'm changing everything to kilopounds per square inch just for simplification of numbers. They tend to get a little bit bigger, especially when you have something like 2400 in one of them. Cool. So now I have that locked in. This axial stress is going to be the same for both point A and B because they're in that same cross section, same face shape, and is distributed equally throughout. Cool. So now for that bending stress, so that's going to be mz, iz, y, m, y, iy, z. I gotta figure out this which one's positive and which one's negative. So I'm gonna be just writing that for now. The reason that I did plus minus and then minus plus is because I know that even though I don't know the signs of them, I know that whatever this sign is, this guy has to be the opposite. Cool. So let's figure out what it would be. So I like to draw my little triangle, y, z. I know that if I have a positive moment in this negative y direction, I should be getting a compressive force on this side, which is negative, and a tension force on this side. Just because I am doing this, so I'm pretty much pulling from here and pushing over here. So what does that tell me? That tells me that whenever I'm using that moment in the y direction, the more I go towards z, so as z goes to infinity, my stress should be going to negative infinity because it's compressive. So what does that tell me? That tells me that this guy is negative, which means that this guy is going to be positive. Nice. But if I don't trust that, I can check also in that z direction. So in that z direction, I know that I have to go this way with the right hand rule. So I know that whenever I have over here, again, I'm pulling over here and pushing over here. So I know that as y goes to infinity, my stress should also go to infinity, which is why they're matching signs. Cool. Now we have that out of the way. Now we're gonna be finding what the actual values for this guys are and what the values for this guys are. I'm gonna start with those moments. My preferred way of doing this one, especially in a test, is gonna be using that vertex form. So I know that my moment by definition is gonna be R cross F. If you're doing FR, you know that you're doing it wrong, so I like to memorize that. Because if you end up trying to do something like that, it's like for real, and that is just wrong. That's kind of like my pointer of how I memorize which one goes with which. So in order to do this, I do have to figure out what my R vertex looks like and what my F vertex looks like. So my R vertex is going to be on that -9 inches for X, and then the Y direction is going to be going 3 inches in the positive Y direction, and then 0 inches in the Z direction. Cool. Then for my forces, I know that I'm going to have that 2400 acting in the negative X direction, when I'm going to have my 400 in that positive Y direction, and I'm going to have 600 in that positive Z direction. And I'm going to have that bounce. Cool. So, a little refresher of how to cross multiply. So we're going to have this one being I, J, and K. The way that you do it is you cover the one that you're on, and then you cross this one. So you do, from I, you go all the way over here, so it's going to be 3 times 600, minus, now I'm going to be going up, 400 times 0. Then for that J, I'm going to cover that middle guy, and the middle guy is always going to be switched around, so I'm going to get negative whatever I'm doing here, so I'm going to get negative, and I have -9 times 600 plus, instead of minus, that -2400 times 0. Last, I'm going to turn this guy up, and I'm going to get that -9 times 400 minus 3 times -2400. Again, what I'm doing is I'm doing that being plus and that being minus. Cool. Simplifying that, I'm going to have this go to 0, that go to 0, just to simplify that. And I'm going to end up with 1800, comma, and this is going to give me 5400. And lastly, this is going to give me, that is 36 and 72. This is positive, this is negative, so and that's poundage. Let's have those two together. Cool. So I was able to find my moment right there, which is great. This already breaks it apart into this being my mx, my, and mz. Cool, nice. So now I'm able to come back to this formula and plug those values in. Oh, actually I'm forgetting that moment of inertia. So for my moment of inertia, I know that for a circle, it's gonna be pi, I'm pretty sure. Yeah. In this case, C is gonna be a radius. So when I plug this in, I should be getting pi 0.5, which that gives me about 0.0491. Whenever doing calculations, you always want to have at least more than one sig fig. In this case, I chose to grab 3 from that in order to simplify, not having to plug everything into my calculator. Try to always grab more than one. That one is almost never going to be enough. Because that's going to give me an answer that is about like anywhere from 2% to 5% off, which can be marked wrong during the test. So we're going to be careful with those. Cool. And because the circle again, IZ and IY are going to be the same. So it seems like I have everything in order to plug it in, so let's do it. So my bending at point A is going to be right here, so A is going to be at negative 0.5, comma 0, because that's negative 0.5y. If you want to be more exact, it's 0, comma negative 0.5, comma 0 for x, y, and z, and my B is going to be equal to 0 in the x direction, 0 in the y direction, and 0.5 in that z direction. Cool. So now for that bending moment, I'm going to end up having that moment in the z direction, which my moment in the z direction is 3600. That y value, which in this case for A is going to be negative 0.5. And that I, which is going to be 0.0491 minus my my is going to be 5400. My z position in this case is 0, so this whole term is going to go to 0. And I'm going to have the same one right here. This whole thing is going to go to 0, and I'm going to end up with a value. Cool. So this gives me 36.67 kpsi. Again, to stay consistent with that, and that's going to give me a negative value because I do have a negative plugged in there. Also, I can kind of look around here and say that anything underneath, because I do have that 2400, that 2400 force acting in this direction, making it my MZ direction. I know that this guy's going to be the one winning, and I know that this has to be compression, so I do know that that has to be negative. Cool. Now for my B moment, I'm going to skip this first term just because that y value is going to be 0. So I'm going to get that negative 5400 times 0.5 divided by 0.0491, which should also be giving me a negative answer because I have that negative in front. It's going to be negative 55.00 kpsi. Cool. Nice. After I have done that, I'm able to actually plug everything back into this formula in order to find those normal stresses. I'm gonna find out my normal at A is going to be that negative 36.67 from that bending, and from that axial I'm gonna have that positive 3.056, which should give me negative 33.613 kpsi. Cool. Which is going to be compressive. Then my normal force in that B direction is going to be that negative 55.0 plus 3.056, and that is going to give me negative 51.948 kpsi, and this one's compressive as well. Cool. So we found the normal mass. Now I'm gonna find that shear stress. For that shear stress in this phase, we're only gonna have one source from it, and that's gonna be torsion. So I'm gonna put it here. I'm gonna erase this moment. I'm gonna rewrite my moment that we found over here. We found it to be 1800, 5400, and 3600. Cool. For that torsion, I'm going to be using that torsion formula that you have for the shear stress, because the only shear stress coming on that face is going to be the shear stress from torsion. So we're going to be doing tau is equal to T R J. You're able to do each direction separately, so you can do, for example, this guy. You would have a torsion in that way, in the negative y direction, so it's going to be in the xy. While in this guy, I'm going to get a torsion in that xc. In this case, what is stops in that portion is forces moment. It's going to be that 1800, just because I was acting at the same region within the face. So we're going to get 1800. R, which is going to be 0.5. J, which J is double of I in circular cases, so about 0.9. 0.09817. Which is going to give us 99.167 kpsi. So again, we're going to have this guy going here and here for torsion and compression.
Nice.
Now for the next part, we're